In pursuit of sharing technical knowledge and just to gear up the new generation of engineers, myself Pranav is here to deliver today's presentation, Power Transformer Part 38. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with on-load tap changer configured with reactor transition. The tap changing components are contained in a heavy-duty oil-filled steel tank which has a flange at the rear end for welding to the transformer. The transformer's tap leads and preventive auto transformer leads are thus to be connected to the back of the tap changer terminal board. The driving component and the monitoring components both are made to be configured in a separate steel compartment mounted below the oil-filled tank with a drive shaft connecting it to the tap changer. The drive motor is digitally controlled servo motor which is precisely monitored and controlled by the tap logic monitoring system. Now let's be on-load tap changer which contains with the following key components. A reactor type tap changer has compiled with a typical design where circulating current is made to be limited by the application of preventive auto transformer. There are two types of switching mechanism for reactor oil type OLTCs. Selector switch type, that is arcing tap switch type tap changer, and number two, diverter switch, which is a transfer switch type tap changer having with tap selector. Designing difference between the two types is lying mainly in the mechanism of transferring the load current during switching. A selector switch type OLTC is just to combine the selection of fine tap windings with the switching of the load current, whereas diverter switch type OLTC has accompanied with a tap selector to pre-select taps without switching current, and in combination with a diverter switch, there is to switch the load from the selected to the pre-selected tap. Let's see the diagram. That is separate oil tank with diverter switch mechanism of OLTC. This will be the tap changer contacts, local control box for driving mechanism, conductor for the supplement windings, basic windings, etc., etc. Selector switch type tap changer. In this type of tap changer configuration, the tap selection and load switching would have to occur at the same time. Tappings of the main winding are thus to be connected to a series of fixed contacts of a selector switch, which would have been of either linear or in circular form, and an associated pair of moving contacts operates to provide the required switching sequence. As the making and breaking currents would occur at the contacts of the arcing switch of a selector type tap changer, so a regular arcing may have been an obvious factor for causing arcing damage to the contacts. Because of the tap changer, including the tap contacts, the switches is mostly immersed in oil, that is transformer oil. Therefore, some degree of oil carbonization as well as contact wear are become inevitable. Such type of tap changer, usually termed as single compartment, is now common for transformers up to about 20 MVA rating. That is, up to 20 MVA rating, there may have been used selector switch type tap changer. Diverter switch type tap changer. For the large transformer, that is above 20 MVA transformer, diverter switch type OLTC, which combines a diverter switch and a tap selector, is mostly used where the tap selector switches do not move when carrying current. The tap selector has two sets of contacts available for tap selection, of which one contact is selected by the diverter switch and is under load. The other contact selects the next tap without switching current. As of design, the next tap position is selected in a circuit that does not carry current, after which the load current is transferred to that circuit by the diversion switch. The tap selector is only to select the tapping, and its electrical contact is therefore to be designed just to carry the rated current of the transformer, but not to make or break the current. Making and breaking of current is generally carried out by two separate diverter switches, usually contained in a separate oil-filled fiberglass compartment rather, so as to minimize the amount of oil contaminated by the process of carbonization. It's a separate container. The concept of a separate selector compartment would have been originated from the design of compartment type tap changers commonly used in the USA and UK. The diverter switch is being driven by an insulated driving arm coupled to the worm gear mounted on the top cover plate. The diverter switches would have to operate to make and break the current and are thus to be mechanically interlocked with the selector switches, which move only when not carrying current, to provide the correct sequence of connection to the winding taps. During the operation of diverter switches, the transition resistors are to be provided for bridging the tap in use of, and the tap next to be used, thereby limiting the circulating current due to the intertap voltage. Now, see the diagram of the diverter switch type tap changer. The main component of diverter switch, one is the fixed and moving main contacts. Number two, fixed and moving transition contacts. Number three, transition resistors. Number four, spring action mechanism. Number five, tap position indicator. Number six, worm gear assembly. Now note, a perfect oil-tight structure is thus to be configured between the diverter switch and the main transformer tank, so as to prevent mixing of oil outside the switch chamber with the oil inside, which would have been contaminated due to the switching operations. Short time rated current limiting transition resistors, which are mounted above the stationary contacts, would have to be configured with nickel chromium wire wound on heat resisting ceramic core bobbins held at both ends by insulation plates. The operational switching time of a flash cycle in case of double resistor type tap changer, which are being equipped with high performance resistance materials, would have usually been less than 75 milliseconds. Operational time of the motor drive mechanism for tap changing activity is approximately of 5 seconds per step. Figure 130 shows a tap selector and a diverter switch assembled together to form a single unit which then be housed in the transformer tank. Tap changer unit is mounted inside the transformer tank, which either may have been hanged from the tank cover plate or supported on end frame. The tapping leads from transformer winding is thereby directly connected to the fixed contact terminals of the tap selector. However, the fixed contacts and the moving contacts, which are usually be exposed to arcing during an operation, are tipped by copper tungsten alloy, and that has brought about an excellent arc resisting characteristics. As the tap changer is contained with oil filled compartment, so the subject tap changer should have to be protected by an oil surge protection relay. As of figure 130, the composite unit is supported by the oil-tight diverter switch mechanism case, which is mounted inside the transformer tank. Local control box for driving mechanism is mounted on the side of the transformer in such a way that the operating personnel can have to operate standing at ground level. The tightness of the control cabinet must be of the protection class IP56 according to IEC 529, that is protected against dust and water jets. The requisite specification of both tap changer and motor drive mechanism are depicted on the front door of the motor drive mechanism cabinet. A motor drive mechanism is therefore to be coupled to the tap changer unit through an external drive shaft and the bevel gear. Motor drive unit is housed in a sheet metal enclosure and comprises of a motor comprises of a motor reduction gear arrangement, B, dial switch for tap position indicator, C, cam operated limit switches for breaking the operating circuit of the motor to stop at end positions, D, operation counters which will register the total number of operations carried out by the motor drive mechanism, and last of all, hand drive for emergency operation. The constructional design of diverter switch type OLTC is based on modular principle and is suitable for star as well as delta connected transformer windings with linear or changeover type tapping arrangement such as coarse, fine, reverse as of figure 131. As the operating sequence of the diverter switch would have to follow the flat cycle, so the tap changer is suitable for bidirectional flow of power. Bidirectional flow of power, which means the tap changer would be most appropriate for application where transformer in which there is possibility of flow of currents from tapped winding to untapped winding and vice versa. Two rotary switches per phase are thus to be provided for tap changing operation where the odd numbered tappings are connected to one switch and even numbered tappings to other switch in such a manner that the two switches come into use in an alternative basis. The reversing switch assembly would thus to be mounted above the selector switch assembly. By switching the reversing changeover selector, one can add or subtract the selected transformer winding, thus doubling its range when the course of fine tap circuit configuration is implemented. Then in that case the reversing switch is referred to act as the changeover selector. This changeover selector would have become isolated from the regulating winding and thus it is being connected to a fixed winding section on the main winding. Hence, this winding section plus the regulating winding would have been added to the main winding in tap voltage steps as per requirement. Therefore, a course changeover selector can add a selection of regulating winding to the main winding and subsequently changing the voltage configuration of all tap selector contacts. Transformer winding, while it is configured with the plus minus tap circuit, then the reversing switch is used for changing the polarity between the regulating winding and the main winding in such a manner that the regulating winding is either added to or subtracted from the main winding. Reversing switch has to provide the same type of contact fingers as that of the tap selector switch and the number of fingers would be dependent on the current rating of the tap changer. Physically, the taps are being located on a regulating winding within the main transformer tank, which is ultimately connected in series with the main winding via a reversing switch. It is to be noted that the reversing switch never breaks the load current. The reversing switch that has to enable the winding to double the number of tap positions without doubling the number of tap leads from the tapped, that is regulating windings. Let's stop here. Further to be continued at the later stage. Thank you. Thank you for patient listening the video. Kindly do like, share and subscribe. Your subscriptions could encourage to post more videos. Also share your comments, feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you.